Welcome. Test, test. All right, looks like everyone hear me. Okay. Test, test. All right. We'll be starting shortly.
One, two, three. Hello. Welcome, everybody. I wanted to welcome you to the SDSC booth at Supercomputing. My name is Frank Würthwein. I'm the new director of SDSC, and I wanted to talk a little bit about what SDSC is all about these days, and point to some of the things that we're doing this week, and give you a little bit of a sense what's happening. So let me start with the mission statement. The mission, as I see it, of SDSC is translating innovation into practice. We are the guys who fill the gap between technology innovations in industry and academia and actually applying those technology innovations to science and making the next scientific breakthrough to industry, advancing the cause of industrial endeavors. That's what we do. And And we do this via versatile computing. Versatile computing is the buzzword for SDSC this year. And versatile computing, what does it mean? It means, of course, we are a supercomputer center. So there's a supercomputer in our name. So obviously we have supercomputer systems, must be, right? And so we're gonna talk about 3 of those systems this week. And the systems I want to point out, there is tomorrow, let me start by the latest one that went into production. It's the Voyager system that we will talk about tomorrow at 10:30. The Voyager system is a system entirely optimized for machine learning and AI. It uses technology from Habana Intel. It is a system that, as it comes today, exists, as far as I know, in just 2 places. You can rent it in Amazon, and you can use it as an academic national user at SDSC. You'll hear all about it in tomorrow's talk at 10:30. The next system I wanted to point out is, of course, our workhorse, our HPC workhorse, Expanse. Expanse, this is now in its 2nd year of production, or its 2nd SDSC event, so to speak. You will hear about Expanse in our booth at 2 p.m. tomorrow, where it is a talk explicitly versatile computing on Expanse, life sciences research, talking all about what are we doing in life sciences at SDSC on our largest HPC system, Expanse. There's also a talk in the Dell booth, Expanse the Dell system. And so Sean is giving a talk in the Dell booth on towards the evening tomorrow. So this is system number 2. System number 3 is the National Research Platform. So while Voyager is AI, Expanse is classic HPC, NRP is a national scale distributed system that is literally deployed across 40-some campuses. You should imagine a GPU infrastructure that has footprint all over the country. Add to it a data infrastructure with content delivery network, data origins, in order to make any data, anytime, anywhere, a reality across the entire nation and the globe. In fact, you will find that NRP has hardware that it manages on 4 continents. And you'll hear more about this at 11. In addition to our name, Supercomputer Center, we have a wide variety of versatile computing things that we are involved in, about a wide range of things. Some of the things I want to point out is there is the Science Gateway effort invented here, so to speak. Science gateways have a long history at SDSC, and there is a talk at 11:30 today about the new Center of Excellence to extend access and in science gateways. Another thing that I want to point out is increasingly SDSC is involved in convergence research. What is convergence research? Convergence research is a term, it's one of these NSF terms and it stands for convergence between technology and social impact, and having multiple communities, multiple domains, cross domain and efforts in order to solve big challenges, societal nature. Think for California, among those big challenges are the big 3 threats to California: fire, earthquakes, drought. We're an institution in San Diego. We're located in California, love living at the beach at the West Coast. Therefore, we have a special focus and responsibility towards the threats that threaten our quality of life. Therefore, we have programs on wildfire research, supporting fire departments, supporting regional fire departments and statewide fire departments. We have research on earthquakes. We have research on the water, on the water availability in California. It's kind of a little known fact that most of our water actually comes from what's called atmospheric rivers. They are storms that bring most of the water to California. So what we live off is literally capturing storm waters, putting it into reservoirs, feeding off the reservoirs. And we have research ongoing that is dedicated to how do you predict the amount of water that the storm is going to dump onto the West Coast, and where is it going to hit? Which reservoir is it going to fill? Which reservoir has to be emptied out in order to be able to fill? How do you manage the entire water ecosystem of California? That's also something that we're involved in, and it fits into the convergence research bracket, broadly speaking. And there's a lot of other things that I don't want to point to every single one of them, but check out you can at the booth over there, you can get a program, check out what we have to offer during the week. The last one I want to point at is CloudBank. CloudBank is a very interesting project. It is actually has as customer not just academia, it has as customer also the NSF itself, the National Science Foundation. Ask yourself, what are the challenges for a federal agency to give out dollars to researchers in the cloud? A lot of it is actually about accountability. You give out cloud money to somebody, are they going to spend it before the contracts run out? How are they going to use it? Can I have visibility into this? CloudBank both serves the NSF and it serves the academic community. It serves the NSF by showing who spent how much, when, in which cloud. It serves the community by allowing them to spend transparently across all the cloud providers. You intended to work with Amazon, but then Google comes out with this really cool new toy, and you really want to use your money there. You don't want to be tied to Amazon. Voila, CloudBank makes that possible. You can move your money around at will between the different cloud providers. You can even move money around into quantum computing at IBM. Funds that you have received in a CloudBank account can be spent on quantum computing at IBM. So in a funny way, it allows the researcher an enormous amount of flexibility to not be tied to an individual vendor, but it allows multi-vendor, including IBM for quantum computing, to be in the game and you to spend your hard-earned NSF dollars one. And I think I'll leave it at that. Thank you very much. Welcome to SC22. Thank you very much.
Yeah. Yeah. Well, it was just like a small, it's not supposed to, it's not even real because like the real is a real quadcopter. But we saw the rotor-rotor interactions. So we went, like we just flipped it and it's supposed to stay permanent in theory. I don't know. That would have been also probably like good too.
Check,
It's
check,
not- so that
check.
was
Yeah? You hear that? Check, check, check. Do you hear me on the mic there? You hear me up there? A little low, a little low. Oh, there we go. Hey, folks, start gathering around for the talk. That's going to be the one they talk about at SC this year. If you go to any one booth talk, this is the one to go to. Learn about the National Research Platform, the most innovative high-performance computing system. Said sliced bread. Hey, Dave. Gonna get started in just a few minutes. There's only a few seats left. Just a couple more minutes before we get started here for the National Research Platform talk. the most innovative high performance computing system since the Cray 1. And a whole lot cheaper. See, check.
Hello, one. Now, is it on? Yes.
Check. All right, folks. Hey, thanks for coming to SDSC's booth to hear about the National Research Platform. We've got a great panel for you today from Frank Würthwein, our director, and our vendor partners who are helping make this a reality. So without any further ado, I'd like to introduce Frank Würthwein, the new director of San Diego Supercomputer Center. He'll give some comments about the system, and then we'll have each of the other folks come up, and then we'll bring them all up at the end for some Q&A with you all. So thanks a lot, and take it away, Frank.
Hello, my name's Frank Würthwein, and I'm the new director. I am the new director of SDSC, and the system that we're about to talk about is very much in the theme of versatile computing. It is following, I'm going to tell you a little bit about the vision behind the machine, and then you hear a lot about the machine and what we're using it for. The vision behind the machine long term is that I'm interested in federating the entirety of academia in one large giant system, one large giant nationally distributed system. We're looking at to create an open national cyber infrastructure that allows the federation of CI at all 4,000 institutions that are engaged in open research. We're talking 3,900 universities and colleges and whatnot, and then about a few hundred probably foundations and national labs and so forth. The vision here is that we create an open infrastructure across all of them, and an open infrastructure for us means that people can do open science, use open data, use open software, and we build an open cyber infrastructure means hardware and systems that can collaborate and build a platform for the entire nation. That would include compute, storage, and content delivery networks, and in the future, devices, edge computing, sensor networks, you name it. Anything that sucks up electricity, uses power to do computing is fair game. The NRP system that you're hearing about over the next little while is an unusual system in that it is both a project and it is hardware, but it's also a community. And it's an important feature of the overall design of this system and the objectives of the system. As a community, it has lots of funded projects that contribute to a shared vision that I've just described. The NRP is therefore owned and built by the community for the community. And what you're hearing about is the project NRP that has the hardware that our partners allow us to put in place. And so the program that it is within is called the Category 2 program in the NSF. This program is designed by the NSF to allow for innovative systems to basically allow centers like ours to explore where is the future of high performance computing going. Can we bring novel architectures into play that are in between just research on systems and production systems? As a result, the NRP will be a 3-year test bed where we get to basically play with the toys that we're buying from the vendors. and have the entire community play with those toys, do R&D on systems, develop new ideas and so forth. And then afterwards, there's a 2-year allocation phase. And we figured that this is a perfect program to put a proposal forward that executes on the vision that I described. And this is what we actually are deploying now. This is what we have deployed and are now commissioning. It is, well, it's a US map, continental USA. Literally what I did in order to write this proposal, I asked myself, how do I tessellate the continental USA with 500 mile circles such that we can create a vision of any data, anytime, anywhere in the country? And so what I've come up with is at the center of every one of these circles is a network cache inside the network backbone of Internet 2. And then there is 3 special circles in 3 parts of the country that are actual GPU systems with a significant amount of hardware. And there is 2 of these systems that are focused around FP32, and 1 system that is what we call our high performance partition, where we're sort of stretching the envelope towards FPGAs, NVIDIA DGXs, and GigaIOs or a composable infrastructure. And so you'll hear more about these systems from our vendors, but the basic concept is that we create something that the scientific community can use to do systems research as well as science research, and where they can do systems research to evaluate, build the next generation domain-specific systems and excel. This implies 5 innovation thrusts, and you'll hear about some of these things as we go through, or ask me anytime afterwards. It includes the composable systems R&D, includes FPGAs as next generation domain-specific systems. It includes a engagement with the entire community. We operate other people's hardware on 4 continents now in the world. It includes an innovative data infrastructure that I mentioned. And all of this is in support of a boatload of science across a wide spectrum. The system, the concept behind the madness of such a large number of science drivers was that we have 5 innovation thrusts, and we want this system to be growing and have an opportunity to grow its user support inside the community. Therefore, we create a matrix between the innovation drivers and the science communities. Multiple science communities have interest in the same innovation driver. Therefore, they form a matrix that they can self-support and scale out to all universities anywhere in the country. That's at least the idea. And this includes global scale experiments and instruments, billion-dollar type facilities, includes campus scale instruments, anything from gene sequencing to microscopy. It includes simulations, AI, human microbiome, all kinds of large number of different sciences, but it also includes systems R&D. There are science drivers in here that come from computer science, whose sole science is actually the engineering of new type of systems. And so we make the entire range from systems R&D of future systems to science R&D of science questions on today's systems. Our goal long-term is growth of the NRP to the nation. There's national in the name for a reason, and you've seen why. By the end of this year, we're expecting to have 1,000 GPUs of all kinds of shapes and colors in this infrastructure. By the 2 years from now, I hope to have 50 petabytes of storage as part of the distributed storage infrastructure that feed the caches. And we want to grow the diversity of the community, and we want to introduce new capabilities. We're doing machine learning at the 100 terabyte and beyond scale. Ultimately, the goal is petabyte scale machine learning. We want to experiment with new types of hardware as nodes in NRP, they can explore that hardware by mixing and matching on the composable infrastructure, and then buy something for themselves that we operate via our bring your own resources concept. And then we want to introduce, attached to it, sensor networks in the future, so that we have directly data streaming from the sensors into the infrastructure, do AI on this, et cetera, et cetera, et cetera. And we're having a workshop in San Diego in February 8th to 10th, where we will define the future of all the new things that we do that I haven't even thought of. And I will hand it over to Alan now.
Excellent. Excellent. Thank you, Frank. So we'll talk about the GigIO fabric system here for just a second. And this is part of the implementation that's at San Diego. So the NP64, right, the floating point 64 system and the HPC system. So a key feature of our interconnect, of our fabric, if you will, is our ability to be able to connect devices to servers and then servers to other servers all across a PCI or a CXL fabric. And the fundamental part of that, the fundamental innovation that's happened at GigIO is our ability to route PCI between servers. And so you can have resources that live within a PCI domain, and you can compose resources into that domain. And then you can also reach across domains, and you can use resources or run jobs across it. So we can run MPI, for example, natively on fabrics. We can run NVMe OF across fabrics, and we can, of course, compose resources. So this is a diagram of what Frank's systems looks like. So here's the San Diego system, the high performance system. And he gave us a really interesting challenge here, right? That they wanted to be able to use a good cluster of GPUs. And so there are 64 A100s in the system. And he wanted to be able to run FPGAs, and he wanted to be able to mix and match those at will. And so you can see he's got a high performance Ethernet backbone. It's what pumps data into this system. And then the compute traffic all runs across fabrics. And what we're able to do is the FPGAs are sitting in what we call our resource boxes. These can be assigned to any server, including the DGX servers, and or to individual 1U servers. And you can also kick off jobs on the 1U servers, and you can run what's called a nickel ring or an MPI ring and take advantage of the GPUs that are sitting inside of the DGXs. And so in summary, I keep it really quick. We'll open for questions, right? The two key advantages that we bring with fabrics, right? So number one, we establish this memory fabric that carries not only computational capability, but also your server to server traffic. And it's literally a memory construct between everything in the fabric. And so there is no RDMA functionality in the network. It's all a DMA transaction. So there's no bounce buffers. There's no language translations, and it's happening in 500 to 600 nanoseconds is typically the latency between any device. And then number two, we heard very early on, please do not give us your interface. We have our own tools for managing our networks and our clusters. Use those tools. And so with Frank at San Diego Super, they have two things that they use. They use a Bright Cluster Manager. And so we are integrated directly into Bright. And so you bring up the console now in Bright, and you can assign resources. You can drop and drag, GPUs or FPGAs to other servers. It's a very nice user interface. And at the same time, there's other groups at SDSC that want to use their automation tools. They want to use, either Ansible they use mostly Ansible playbooks. And so the group that uses Ansible can continue to use Ansible. The group that wants to use Bright uses Bright, and we do the synchronization between the two. So if you drop and drag, if you do something with Ansible, you actually can watch on another monitor, you can see the bright manager changing. And so we manage that interaction. So you don't have to, we keep that in sync. So we're down the way. If you have questions for us, come see us. We're at booth 539 down that way.
Thanks, Alan.
Thank you, Alan.
Now introduce Ryan Emmerich. He's the Senior Account Manager for Applied Data Systems, which is providing the hardware at the San Diego site. Take it away, Ryan.
Thank you, Sean. Thank you. I think today what I'm going to do really briefly is just introduce Applied Data Systems and our involvement with SDSC and the NRP project as a system integrator, HPC system integrator. We're located in San Diego. Let me just pull up the slide. Located in San Diego. So strategically positioned, I would say, was at San Diego Supercomputing as well as a supercomputer center, as well as GigIO to be able to be a good system integrator of choice, to be able to put this cluster together, composable cluster using GigIO technology together for SDSC and NRP funded by National Science Foundation. So we're very honored and feel very privileged to be involved with this project. So I'm just quickly going to go over who we are, what we do, and what our involvement was. Applied Data Systems, we're a system integrator with expertise in high performance computing. Computing interconnect, storage, file system, middleware. So we put all these things together, make sure they work together, test them before shipping out and making sure that they work as smoothly as possible when they land at customer sites. Systems customized to your needs, fully tested in-house. So we do build and test, make sure we work out those kinks before we send them out. On-site engineering at time of implementation and white glove service. This is something that a lot of our customers love, which involves us meeting the cluster on site and installing the cluster and making sure that it's connected properly and working properly before deployment. We're headquartered in San Marcos, San Diego, privately held, but we have another facility, a customer integration and manufacturing facility, CIMC. That facility is in San Diego, Poway. Our business philosophy is to be the #1 high performance computing system integrator partner by providing custom solution focused technology to our customers and exceeding their expectations regarding quality and service. This just kind of goes into our business model when we engage with our customers from a sales perspective, providing these turnkey solutions for computing and storage. Consultation, coming in and consulting with the customer, what may work best for their applications, given lots of different factors. Maybe sometimes that includes what they're comfortable with as far as technology and different manufacturing vendors that they like to have. We are agnostic to a point where we could use lots of different technologies depending on what works best for the customer, given their environment and their history and things like that. Engineering, come in and help consult from an engineering standpoint and help build and configure these systems so that they work best for the applications from a custom standpoint. So we do that through various partnerships with white box, as well as OEM partners like Lenovo and Dell. Once again, just depends what works best for the customer. System integration, so we build it all in our customer integration manufacturing center in Poway, and we build the systems, rack and stack, load them with software, and make sure that they're working smoothly to the customer specifications before shipping out. Deployment and warranty and support. So single throat to choke for support for all the systems. There's a lot of different technologies and a lot of different partnerships that go into building these solutions. We juggle all that and provide a single throat to choke for support. If support's needed, a call is a first tier call support is brought to Applied Data Systems, and then we kind of farm it out from there to make sure that the customer is taken really well care of. Some of this will get a little redundant, so I apologize. ADS's partnership with SDSC. This just briefly goes over our involvement with SDSC and the NRP project. Our real role in the project, which continues today. So it's not just dropping off, it's continuing to work with our customer and continuing to do development and enhancements through some work to make sure that the cluster is continually being enhanced. So our value as a strategic partner, assisted to create custom BIOS for GigIO compatibility and enhancements. We continue to do this. There's continuing to be functions and enhancements that are unlocked. So that'll be a continued thing, but it's a value that we provide in the partnerships that we have to be able to put the right players together. And sometimes these are some of the better developers at our particular partnerships, to put them together to be able to build a system that is as cutting edge as this GigIO composable infrastructure project. Identify and implement the right mix of OS, software, firmware levels Sounds a little simple, very hard, especially for newer technology. So we vet and go and work with our partners to ensure that we're building and configuring a cluster that's going to work. ADS expertise makes HPC easy. So this basically goes for all our different projects that we work with our customers, most of them. We rack and stack, labeling all hardware cables in our CIMC production facility. Software implementation and configuration speaks for itself. Extensively stress test to weed out any failed components before customer delivery. I think this is crucial. We don't want any failures after the system comes on site, nor do our customers. We don't want it to be a support nightmare. So it's very important for us to test very strictly, very stringently to really weed out all those failed components before they fail at a customer site. Allow for customer remote login and testing and validation before ship out. We think this is very important. Our customers really enjoy this because it allows for less tinkering when the systems actually come on site. So we do allow that service at Applied Data Systems. White glove delivery, on-site install, and PS if needed, speaks for itself. And then single thread to choke, like I said before. And I just listed some of the main partners that were involved with this cluster to include GigIO, AMD, NVIDIA, Xilinx, Gigabyte, and Bright Computing. This is just I think we've already gone through this, but this is just a really quick general overview of the cluster again. Customer, San Diego Supercomputer Center, National Science Foundation as a granting agency, program National Research. And as you can see, there's different resources, 8 HGX nodes, which each with A100, eight A100 GPUs, featuring NVLink and NVSwitch to be composed. 6 gigabyte AMD EPYC CPU only nodes, 4 all NVMe nodes, 4 of the GigIO APA boxes, the resource boxes, which each contain a Xilinx U55C FPGA. Each node contains a GigIO Fabrics adapter, a GigIO Fabrics PCI switches, Bright Computing Ubuntu 20.04, and supports MPI and NVMe-OF. So that is all I got. Thank you. Supermicro.
Thank you, Ryan. Next up, we'd like to introduce Max Chung. He's a staff solutions manager at Supermicro, and they are providing the systems that Frank pointed out at the remote sites at University of Nebraska-Lincoln and the Massachusetts Green High Performance Computing Center. Take it away, Max.
All right, thank you, Sean. Hello, everybody. I hope you guys are having a great time at SC 2022. So my name is Max Chung. I'm a staff solutions manager. I work with Sean and Frank and to build this NRP platform. Our team, we managed to build and install 2 other clusters, one at University of Nebraska, Lincoln. The other one is MGH PCC, Massachusetts Green High Performance Computing Center. So it was such an honor to work with top scientists like Sean and Frank and Amit to build this wonderful national research platform. So I'm gonna show you the process we go through to build these 2 clusters. Okay, so basically all of the rack level solutions, we will go through these 5 rack integration processes. So from the beginning, we work with the customers, in this case, SDSC, on the application analysis to learn what kind of workload we're gonna run on these 2 clusters, right? And then we decide on the system configuration to come up with a power budget at the node level as well as the rack level. And then we will create a BOM, bill of material, including everything we need to build the cluster, including the switches, PDUs, cables, and the racks based on the requirement. And then we'll design the rack layout based on the data center requirement, right? And then the second phase, we do the assembly. So all the nodes will be assembled at Supermicro production line. And then after the nodes have been assembled, it will be transferred to our rack integration facility. We'll do the rack stack. So, and then we will put the switches, PDUs, and everything into the rack, and we do the labeling and cabling. And then the third phase, we'll do the configuration. So we will check the BIOS and decide on what setting we're gonna put onto each of the nodes. And then we will help manage the firmware because each node has a lot of components inside, including the firmware to be installed into the GPUs, NIC cards, and BIOS and BMC. So we will make sure all the firmware, they're all uniform across different nodes, across different racks. right? And then we do the switch and the network IP configuration to make sure depends on the customer network design. If we want to run at all layer 2 all out, or we want to layer 3, do some ECMP across all the nodes, right? And then finally, we'll load the network we'll load the operating system on all the nodes based on the requirements. For the NRP, we load Ubuntu 2004 onto all nodes, right? And then the fourth phase, we'll do the testing. So we test all the nodes, all the components to make sure we want to weed out all the weak components, to identify them early, and then we replace them before we ship them to the customer side. All right. And then we do full rack burning to make sure everything's fine. We meet customers' performance objective. And then at the end of this phase, we'll get a test report to identify all the components can be seen from the operating system view. And then we'll have a performance report as well based on customers' specified performance benchmark testing. And then the last phase is logistic. So we will do the asset labeling and create the document for the cluster. And we'll do the crating, put everything into the crate to ship to the destination data center. And we'll do the white glove service to help customers install the rack level solution into their data center. All right. So here are just some of the examples of our rack solutions recently we built. Recently we see we are building most of the rack solutions. They are mostly GPU based. So on the left hand side, the two racks, they are the GPU racks right now we are building. So for the SDSC NRP, it'll be similar to the first rack. It's all GPU servers. And the one we are showing here is actually 2U2 node GPU systems. And the second rack, we have a 4U GPU systems with some like a UPS on the bottom side. This is different design. And then we also help customers build high performance, high density compute racks for the third rack and third and fourth racks. This is a big twin base, and then we have a super blade based high density compute racks. And then also we help customers build storage racks. You can see we have like this is all 90 bay SSG system we have here. This is five systems head nodes with 2 SSG attached to it. And then lastly, this is the industry trend. We start to help customers to build liquid cooling racks because right now the new GPUs, new CPUs, they are 400 watts, 500 watts per card or per CPU. So the normal data center cooling capacity won't be able to handle this. So that's why we are seeing the trend and we are using more and more liquid cooling solutions. All right, lastly, this is the phase 3 of NRP, 5 racks for 2 clusters. That's when we are being rack and stack and in our facility. This is the last slide. Thank you, everybody.
Thank you, Max. If I could ask the other panelists to come on up now and grab a seat for a little Q&A. Ryan, where you are? So, I just wanted one thing I want a little commentary is that, at the beginning, Frank talked about, building a system for the community, by the community. And so we have here multiple vendors, and we kind of figured if we can't learn how to work with multiple vendors on a single project, it's unrealistic for us to expect that we could have this magic BYOR 4,000 institution idea that Frank has. So we're demonstrating it. We're putting our effort into working with all these great vendors, and they've all been terrific. And so just want to thank you all for being great teammates and working through all this innovation. I know there's a lot of challenges in a project like this, and it's great to soldier on. I'm not sure we'd get that with other partners. So do I have any questions from the audience here? Any questions, comments about the work we're doing? I've got one right here. Can we get a microphone over to that gentleman?
So I'm a little bit curious about, have different kind of architecture, different kind of processors and distributed, and how do the applications map to those? I mean, different applications supposed to take advantage of different architectures. And so I'm just curious about that.
So what I'm here, did you hear that, folks?
1, 2, 3. Okay. So initially, one of the beauty of this, of the solicitation that we're responding to of the program, is that there's a built-in R&D phase of 3 years to, we start out with what exists today and walk ourselves to over the next 3 years to where we want to be. And in the process, we work with our partners to make it happen. And so initially, we're going to manually configure favorite node architectures, and then over time, make what is initially manual, dynamic, build it into Slurm, and I'm handing it over to Alan to talk more about that.
Great. Can you hear me? Okay, good. So the short answer is across the Fabrics network, the applications don't know that the resources live in various places, right? So if we've composed resources to a given server, to the application that's running on the server, it has no idea actually where the resources live. And so the application just, it recognizes that I've got 16 GPUs or I've got 16 FPGAs and I've got a certain amount of storage that's been assigned to it. And so it just assumes that's the size of the server. Now, if you're running, let's say, an MPI job, or you're running a nickel ring, that's easy enough to kick off between multiple servers. And once again, if you're running a nickel ring or you're running an MPI job, you've set up that construct across servers anyway. And once again, it doesn't know, it doesn't care where the resource lives.
Thank you. I've got a question for our two system integrators. So we learned a lot about doing this stuff and on our fence, but as the system integrators who are sort of trying to work with new technology, what is this? How does this help your company? If you're working with an organization like SDSC, where we're pushing you pretty hard, does it help your company? Does it hurt your company? Tell me about it.
I'd rather not say. No, no. This is. I think this is part of what we're usually very used to with our customers, is being. Hello. Yep. So as an HPC system integrator, I think we're very used to being guinea pigs in a sense, and having customers that are guinea pigs in a sense. A lot of these projects are very emerging. They're emerging new technologies, and a lot of times we learn as our customers learn, as our partners learn. So this was a very edge type project, and we learned a lot. So there is some benefits to that. Although there's a little more hand-holding and a little more work that goes into that. I think that we're very well geared with our partnerships and the relationships we have with those partners, as well as the relationships that we have with our customers, and the way that we are organized as an organization to learn as we do that and do it as well as possible. So there is a benefit.
All right. Actually, for the NRP project, it's pretty standard for us. It's uneventful, I would say, compared to the Voyager project we delivered last year. Yeah. So this is the standard operations. Like I described 5 phases, and we go through all of them, and then we deliver them uneventfully.
Max is talking about Voyager, which is another system that Supermicro helped us with, and Amit and some others will be talking about that later on in the show. Other questions? Do I see any hands? I know there's got to be dying questions here. We've got 3 sites down, and according to Frank's map, we only need 3,997 to go, and then we'll have NRP fully deployed. Frank, I wanted to ask you, what's going to happen at this workshop in February?
So at the workshop in February, we're trying to bring the community together across not just the 3 sites, but across all the sites that currently have hardware donated. There's going to be on the 8th, there's going to be some we're starting on the 8th of February in the afternoon. There's going to be some workshops in the afternoon on different topics, including a workshop for new institutions who want to join this. How does it join? How does it benefit you? There's some amount of CIO training, so to speak, on what this is all about. And then in the evening of the 8th, we're going to have a big scrumptious feast at the Birch Aquarium and celebrate the retirement of Larry Smarr, which is co-located. He's one of the PIs that we built this on. We're sort of building on the shoulders of giants, so to speak. And so Larry's retirement party is at the Birch Aquarium on the evening of the 8th. Then on the 9th is the main day where we have lined up a number of different panels as well as presentations. We'll talk about the science that it does. We'll talk about how the system, what are the challenges in addressing the needs of under-resourced and underrepresented groups, meaning under-resourced institutions to be accelerated via NRP, under represented communities having access via NRP. That sort of thing is a big topic of the show. And then there's going to be a dedicated session on the sensor networks that I talked about. We'll have a session where that is entirely dedicated to how do we bring sensor networks to the NRP, to the backhaul network, to the compute, bring compute out to sensor networks, et cetera, et cetera. What are the use cases? What are the challenges? That is one of the things that is going to come up there. And if somebody has a topic that they want to pitch for the NRP, I'm all ear.
So that was a pitch to come to the workshop in February, if I ever heard one. So that was great. Thanks a lot, Frank. Any other questions? I've got one last one. Again, I want to ask this kind of our vendor partners, and that is, so kind of you're here at SC, you know, and you're building systems today, but you know, what's exciting you about what you're learning and going to be building next? I mean, what's the big deal that's coming for y'all that looks interesting, challenging, and exciting?
Well, you know, Supermicro is basically a hardware company. We help customers build their infrastructure. What I would really like to know is how you guys utilizing it. So when delivering the NRP, I talked to the lead system administrator there. I learned you guys are gonna use there's a web portal called Nautilus as a front end for all the researchers to submit their workload, and then you have a Kubernetes-based dispatch to send all containerized workload across different sites, right? I think this is basic. I really love to see that kind of implementation, how to utilize the hardware, you know, to contribute to the community.
Terrific. And when you're all done here, Dima can tell you all about that. He's our Nautilus guy.
When's that workshop?
So for GigIO, we're looking forward now to PCI Gen 5 and the introduction of CXL. And we talk about the march of composability and effectively being able to treat your servers as a collection of Lego blocks. And you can then start to think about CPUs and memory and storage and GPUs and any other kinds of accelerators as completely separate entities. And today we can do all of that except for memory. And we can do some things with memory, but with CXL, we look forward to doing basically all composition across memory as well, and fundamentally rewriting how it is that people connect and develop a cluster in a group of resource.
I'm going to repeat some of the stuff that Alan said, but I think the composability aspect of some of the stuff that we're doing and this type of project is really exciting to be able to compose the resources beyond what you can do in a single server itself, you know, with the multiple GPUs and NVMe resources, and really essentially build these extra large computers that we've never seen before. And CXL in particular, I know that's on your roadmap, Alan, with GigIO. Really interesting and exciting to get into starting to compose the CPU and starting to compose the memory aspects of those systems. I think another really, you know, containerization and seeing where that goes in HPC is pretty interesting. So really looking forward to that. But as a system integrator, it's everything: the connect, the storage, the compute, and all the software that allows to be able to push your data, to create the data quicker and to be able to move your data quicker is very interesting to us. So quantum computing as well. You know, we got one eye on that. That's pretty exciting stuff. So we'll see where that goes. But yeah, really everything, every day is something new and exciting.
Great. So let's thank our panelists, please, for the talk. Thank you very much.
Good morning, everyone. My name is Mike Zentner. I'm the director of the Sustainable Scientific Software Division at SDSC. And the talk that was advertised today was to talk about a new project called SGX3, which I will talk about, but it also fits into a greater context of cyber infrastructure services that we offer at SDSC. And also a whole suite of things related to science gateways. So bear with me as I kind of go through this whole ecosystem of things that we do here. Now, I'm specifically going to talk about software cyber infrastructure, not the hardware cyber infrastructure that you just heard the discussion about, but the software that runs on that cyber infrastructure. And I wonder, when you think about software cyber infrastructure, what's one of the first questions you think about? Hopefully that question is software development. Now, that's just one piece of software cyber infrastructure. And what I'd like to talk about today is an entire chain of activities that go along with that central activity. The first of which is pretty obvious for most people, that happens before that, which is technology planning. And I'll go into more detail about exactly what that entails in just a few minutes. After that, there's another thing that comes later. And that thing is, how do we disseminate this software that we've developed? What are the mechanisms for that? And particularly, how do we do it at scale? Now, there's another one that comes even after that, which, if you've been on any review panels, you would probably guess what this might be. That is sustainability. And again, we'll go into that in a little more detail too. But what I'd also like to contend is that there's another question that comes before all of this stuff. And that question is also related to sustainability. Okay, so sustainability hits both ends of this process of creating software cyber infrastructure. Now I'm going to talk in a little bit of detail about each one of these. In terms of software development, we run into problems when we do this in an academic setting. One particular problem is the continuity of staff. As we win awards, we hire staff, and as the awards come to the end, the staff often departs and leaves us with a stack of software that we don't necessarily know what to do with. We also struggle sometimes with having professional development processes in place, and of course the workforce development that comes along with that. On the technology planning side, we would typically think about software architecture as one of the first things we have to address, but some things that aren't thought about at that early stage as often as they should be are user experience design and analyzing technology for gaps, and in particular, what kind of technologies are out there in the marketplace that can be used to fill those gaps. At the dissemination point, we have to look at other things like solution packaging. Creating the software itself often isn't enough to get it adopted in a community. So what do we need to wrap around that software for a larger community to actually use it? And once we've done that, how do we actually build a community, and what's the mechanism by which we deploy this software? On the sustainability side up front, sometimes we need to do a little bit of work to understand, is there really a gap there amongst the community we want to use this software, that they would actually use it if we were to create it? Does it address any user pain points in a big way that would make them do that? And even at this point in time, it's not too early to start thinking about the financial viability ultimately of the software you're creating, which then comes to what we normally think about with sustainability, which is, how do we go about marketing and selling the software we've created? And maybe probably one of the most vexing things about this is, what do we need to do to be able to continue to maintain it and keep it up to date? When the grant is finished, it's a difficult thing to do. So if I paint this entire picture, and if you buy into this picture, this is actually a pretty expensive proposition to do. And most of our grant awards don't really provide sufficient funding to address all of these activities. Now our solution to that at SDSC is to create several pooled service organizations that help us provide these kinds of services by sharing them across many different projects. And these are some of the logos you see up here that I'll talk in more depth about for each one. So I'll start with the RevUp program. And what RevUp is really about is helping scientific software creators think about how they might generate enough revenue from their projects to be able to do that maintaining and updating and keep the software alive after the grant is finished. It's not about commercialization, although sometimes people do choose to go that way. This is an offering at SDSC. The email address is up here. If you're interested in it, send us an email. But it's really broken into two stages. At the very front end of that picture that I just showed, it's really about education and one-on-one consulting to help people who are thinking about a cyber infrastructure investment really think about it from the standpoint of just like they were going to start a small business. So how do they go about analyzing what are the ultimate sustainability prospects for the software they're about to create? Then at the end of that process that I showed, it's really all about productionization, or that packaging step that I mentioned. How do we package it for people to be able to use it? How do we go about operating it? For example, if it's a software or platform as a service, what do we need to have in place to run 24/7 reliable operations for this software? And of course, selling it. And these are all things that the RevUp program helps with as well. Now, I want to focus a little bit more on this dissemination, particularly at scale, and how one might go about doing that. I'd like to make a case that maybe one of the better ways to do that is through a science gateway. Why? Well, if you want to sustain a piece of software, you need users. Science gateways provide a very simple interface, typically for users to access complex software. And ultimately, science gateways allow many investigators who are contributing software to a common domain to share the load of sustainability planning, as opposed to everybody trying to solve that problem by themselves. So if you don't know what a science gateway is, I'm going to stop here for a minute and go into a brief discussion of what a science gateway is. It's all about establishing connections. It's a web-based platform for connections in the conduct of science. Historically, how these things typically looked was it was a place or a website that allowed complex software to access HPC systems in an easy way for people to be able to use those systems that might not otherwise have the skills to do that. But it quickly grew out of that. People started to realize that these gateways didn't just serve a few people, but they actually generated very large audiences. Many people who had nothing to do with the writing of the software or the operation of the HPC resources bought into this, and many researchers started using these science gateways for a variety of purposes. They also had a translational effect. As researchers put codes on science gateways, students started to use these in classrooms. And so now we see tens of thousands of students a year running complex software in classroom studies because it's been made simpler by science gateways. Somewhere along the way, science gateways also grew to connect to expensive instruments, and particularly the data that come off of those instruments and providing access to those data, which brings up the notion of data-centered computing. And nowadays, science gateways are hosting large amounts of data and codes that can operate on those data in such a way that people don't have to download massive amounts of data to their own resources, download codes, compile them, and install them locally, but they can accomplish all this on a gateway. But one of the things people don't typically think about in all of this technology is maybe one of the more important things that gateways do. They have evolved to incorporate a lot of collaboration features that help establish networks of researchers addressing problems that might not necessarily normally meet each other. So that's what a gateway is. Are they important? I'd say yes. Do they get used a lot? This is a picture of one gateway, the NanoHub. And this is a day and night usage of NanoHub over just a few day period. And you can see these resources are getting accessed and simulations being run all over the world, day and night. Do they have a scientific impact? The Cypress Gateway hosted at SDSC, this slide is actually out of date now, has supported over 10,000 publications that cite that science gateway as contributing to their research. That's a big impact. Do they facilitate collaboration? Looking at about 2,500 publications that cite the NanoHub, we can see the establishment of co-authorship networks amongst these researchers and even sub-networks within those larger networks, in addition to the individual contributions that are also done. Do they have a financial impact? The Protein Data Bank, for example, undertook a significant financial study and found that it would require $16 billion to recreate the assets on that science gateway. So they have all of these impacts, but how I would think about them most is science gateways are really an engine for broader impact. They're a way of propagating the results of a few to the many in a very rapid amount of time because of the simplification of those results for many people to use. And as I already mentioned, they are sustainability habitats for this research as well. These codes and these researchers, when banding together under the common umbrella of a single gateway, actually have a much greater chance at sustaining their software than everybody going it alone. So if you're thinking about building a science gateway, let's talk a little bit about the software development and the technology planning that goes into this. And I'm going to start by talking about it in the context of a software framework for science gateways called HubZero. It's something that we run at SDSC. It's been building gateways since 2002, so it's actually quite a long time, 20-year anniversary this year. It's composed of three major capabilities. One for communication and collaboration, two for publication and knowledge dissemination, and three for all of this middleware that allows sharing these computational resources and data access and so forth. As we look at the kind of gateways that people build with this software, they vary in personality greatly as they use different aspects of these capabilities. They support currently over 20 disciplines by 18 organizations and many others using it in an open source context. Now, HubZero works with researchers in two different ways. First, as a member of a sponsored research project team, so when intellectual contribution is needed, we act as a part of that team, either as a sub-awardee or a subcontractor. But also, secondly, we offer a service called a no-hassle hub, which is basically full-service science gateway operation. We handle all the IT details and all that mess so that the scientists can work on the science and the community building while we handle the IT stuff. And we typically do this at a much lower cost than an individual project could do it, at about less than a third of the cost of an FTE. And that's actually a pretty good deal if you've ever tried to do this before. Now, focusing more specifically on that software development piece, one thing about being 20 years old is that sometimes that means we support code that's 20 years old. And when I first thought about this, I thought, how embarrassing is it to have code that's 20 years old? But then, glass half full, I thought, well, how satisfying is it to say that you've sustained something for 20 years? Not many projects can boast that that occurs, right? And so we thought, that's actually a competence that we have. And how should we go about exploiting that? And so what we've done is we've divided the HubZero group into two different divisions. One that's actually responsible for the ongoing platform, and the other that does nothing but professional software engineering. And in a way, HubZero is a customer of that professional engineering group called SDX. But SDX isn't there just to serve HubZero. It's there to serve, in the larger context, many CI projects. So HubZero continues to be a platform on which people can build gateways, but SDX becomes a group and a platform that many can solve this problem of having stability of a workforce because it's providing that workforce for many different projects. And so that same workforce that was there 5 years ago is still going to be there 5 years in the future, assisting with sustaining those cyber infrastructure projects going forward. Now, if I've at all convinced you that science gateways are a good way to do this deployment, dissemination at scale, let's talk a little bit about some of the software development that goes into science gateways and building science gateways. We have two entities that are involved in this. One is called SGX3, which is Center of Excellence for Science Gateways. The other is a Science Gateway Community Institute. And I'll talk about both of those things here in two separate discussions. First off, the Science Gateway Community Institute was created because if you wanted to build a science gateway at the time, about 6 years ago, you could say, fortunately, you're not alone. There were a lot of science gateways being developed, about 600 of them we could catalog, so there's actually a lot more. Fortunately, you're not alone because there's a ton of technologies out there to help build science gateways. Unfortunately, you're not alone because there's a ton of technologies out there to help build science gateways. And it's really, really difficult to understand which technologies will help you do what as you try to put this web presence for your research together. And oftentimes when people were faced with this problem, their first reaction would be to say, it's just a website. How hard can it be to create a website? And for 2 months, it's really not that hard. At 6 months, it gets a lot harder. And in a year, when you want to turn it on and have it available 24/7, it's actually very hard to do that. And so the Gateway Institute was formed to address this gap in sort of developing a community around gateways, understanding the knowledge and awareness of what you could do to build a gateway and do it efficiently and sustainably. So SGCI has 3 major categories of service. The first is in support for building science gateways, and that largely includes hands-on technology development support, but it also includes other things like usability design that I mentioned earlier, sustainability consulting, and the Gateways catalog that I just talked about a few minutes ago. On the education side, it provides both short-term and long-term educational opportunities in the form of week-long summer programs, as well as full summer internships and even full academic year internships where we place interns with Gateway projects to accomplish real things in those projects. And then networking and community was also a very big part of the Science Gateway Institute, which had the usual things with blogs and forums and partners and affiliates, but also has an annual conference that is unique in that it brings together different domain sciences under the common umbrella of creating science gateways. Now, we just had our first in-person conference in October in San Diego since a couple of years ago. And we're going to continue that next year in Pittsburgh. So if anybody's interested in this, see anybody in the booth here wearing this shirt or an orange colored shirt, and you can get on the mailing list to learn more about that. Now, SGCI is actually in its final year of NSF funding, but what's happened is we've also newly been awarded this Center of Excellence called SGX3 to extend, expand, and exemplify good practices on science gateways. So what does that mean? So people have asked me, oh, that means that SGCI just got more funding, right? And the answer to that is no, that's not what happened. SGX3 is a very different thing than SGCI. The next question people ask is, well, then are you going to close down SGCI, shut the doors on that because you've got something new now? The answer to that is also no. Now, why would we do that? Because when we look back at the history of SGCI, we've compiled a great list of success stories of SGCI. And you can find in our racks back there a storybook that has an extensive list of about 50 or more consulting engagements that the SGCI has been involved in and what we did for those projects, what the impact was, and so forth. So I encourage you to go back there and look at that. So what does that mean in terms of these two entities? They continue to operate together, but you can think of SGCI as a helping entity, SGX3, and SGCI as a building entity. SGX3 is all about helping the community develop, helping develop workforce, starting to analyze the future of what science gateways should be. SGCI is all about helping people build science gateways. This is generally a consulting organization where you can partially or fully outsource the creation of a science gateway. Think of it as pretty heavy touch consulting. So SGX3 is the new NSF funded entity. So the services that you get from SGX3 are funded by NSF and they're available to you at no cost. They include all of the community building activities I talked about, and also light touch consulting in terms of technology architecture and sustainability. And importantly, SGX3 also has these things called blueprint factories, which are 18-month sessions where we take equal numbers of CI professionals and domain scientists and put them together to sort of study what the next generation of science gateway capabilities ought to be to support those communities. We've already got some of these blueprint factories committed to study the access and path projects and what kind of capabilities are needed to greatly broaden access to those projects for people who wouldn't otherwise be able to touch them. And we've also got the domain science activity for the Materials Genome Initiative planned. And finally, we have a special blueprint factory on sustainability services that we're looking at many of the consulting engagements we did with SGCI and turning those into a blueprint for others to look at how they might address sustainability for those projects. Then on the SGCI side, everything there needs to be client funded. And basically what that is full or partial outsourcing of a software development team. So if people are struggling with how to get continuity in software development, this is a place where they can get it. So if I've had any success in convincing you that this landscape of things you need to do for software cyber infrastructure is very complicated, what I'd like to also convince you of is that we have worked very purposefully to develop a set of service organizations to assist with this. Any one of these things is available to anyone inside or outside of SDSC. And if you're interested in it, approach anybody, like I said, in one of the green shirts today or in one of the orange shirts a little bit later in the afternoon, and we'd be happy to talk to you more about it. And with that, I'll stop.